Assalamu alaikum. So inshallah today we'll end up with the revision on chapter 7 and we'll learn inshallah today how to calculate the entropy generation within the system through what's called the entropy balance. So actually we call it entropy balance, not entropy conservation, because entropy is not a conservative property. It can be created due to actually the losses within the system. Some entropy can be generated within the system, unlike mass or energy, which cannot actually be created or destroyed based on the law of mass action, which says actually mass and energy cannot be created or destroyed. But in case of entropy, due to the losses within the system, like friction losses or heat transfer, some entropy can be generated within the system. That's why we call it actually as entropy balance, not entropy conservation. Type, if we do have actually any system, if we do have entropy input to this system through whatever mechanism actually for entropy transfer, and we do have entropy out of this system, and within the system we do have actually the change of entropy due to the transfer or entropy, and also due to the entropy generated within the system, entropy generation, due to the losses within the system. So like mass, actually we can just make actually this balance. We can say actually entropy in minus entropy out of this system. This should equal to actually the change of entropy of this system. But as we said, entropy is not a conservative property. It can be generated within the system, entropy generation, due to the losses within the system. So in this case, the main difference between the mass conservation or energy conservation and entropy balance is actually the term of entropy generation, S generation, which is actually the main term that we need to calculate. And this is actually what's called the entropy balance. This term actually calculates the total entropy. It should be calculated in kilojoule per Kelvin. Also, like the mass equation or any energy equation, we can consider the rate form. So we can say rate of entropy in minus rate of entropy out plus the rate of entropy generation within the system. This should equal to ds by dt within the system. And in this case, the rate of actually entropy generation is calculated in kilowatt per Kelvin. This term d by dt, as you know, a steady flow mean d by dt is equal to 0 for any property. So this term should equal to 0 when we do have actually a steady flow. Okay. But what are the mechanisms for entropy in or entropy out from the system? Actually, entropy in or entropy out from the system can transfer through what we call, actually we do have two main sources for the entropy transfer. It can transfer due to heat, and in this case actually the entropy transfer due to heat is equal to the heat transfer divided by the temperature, assuming actually this heat transfer is transferred under constant temperature. Let's say we do have more than one source of heat, so in this case we can add the summation and we can just say Qk over Tk. Qk is the temperature coming actually from the surrounding, and Tk actually is the surrounding temperature, which should be given if we do have a problem or something. If we do have actually more than one source for temperature, so it will be actually the source number 1. Qk is just regarding numbering. So it should be Q1 divided by T1 divided plus Q2 divided by T2 and so on. Usually we do have only one source of temperature, and usually actually it is the surrounding temperature in most of the application. This is actually the first mechanism of heat transfer. The second mechanism for heat transfer, the first mechanism for entropy transfer. The second mechanism actually for entropy transfer is transfer due to mass transfer, and in this case the entropy transfer due to mass transfer is equal to mass multiplied by the specific entropy. Mass multiplied by specific entropy. Entropy actually cannot transfer due to work. So we can just replace this term Sm minus S out by actually the entropy transfer due to heat, which is Q divided by temperature. And in case when we do have mass transfer, we can just replace this term also by mass multiplied by the entropy. If it is input to the system, so it will be mass in multiplied by entropy in. If it is leaving, so it will be mass out multiplied by entropy out of this system. Let's apply this actually in case when we do have, let's consider a closed system and open system. In case of when we do have a closed system, we don't have actually mass transfer. So in this case, the main mechanism for entropy transfer, or the only mechanism for entropy transfer, is the entropy transfer due to heat transfer. So in this case, for closed system, we have actually talked about closed system like rigid tank, rigid vessel. We do have a substance in a piston cylinder device. We have spoke about it in chapter 4. So you know about the closed system. So when we do have a closed system, we don't have mass transfer. In this case, mass is fixed, so we don't have entropy transfer due to mass transfer. So in this case, we can just say entropy in minus entropy out of this system should equal to the change of entropy of the system plus what? Plus the entropy generation, which we need to calculate. So from this equation, we can say the entropy generation for a closed system should equal to actually entropy out minus entropy input to the system plus the change of entropy of the system, which can equal to mass multiplied by specific final entropy S2 minus entropy S1. Type this actually term Sn minus S out, we said this is a mechanism of entropy transfer. It can transfer by heat, it can transfer by mass. In closed system, we don't have mass transfer, so this term can only be replaced actually by the heat transfer, the term of entropy transfer due to heat transfer, which can be replaced by Q over temperature. Okay, so in this case, we can say the entropy generation for a closed system will equal to mass multiplied by specific final entropy of the system minus initial entropy, specific entropy of the system minus summation of QK divided by Tk. And this is the equation that will be applied for a closed system in order to calculate the entropy generation within this closed system. Type this term Qk over Tk, it will be substituted with its sign, it will be positive. If the heat is added to the system, you have to actually substitute with the sign. If heat is rejected from the system, we have to put here negative sign, so it will be negative, negative will be positive. So this term is negative when the heat is rejected, and actually it should be 0 when we do have an adiabatic system. When you say we do have an adiabatic system, this means the heat transfer is equal to 0. And this Tk should be actually the surrounding temperature, and it should be given for you. Okay, this temperature should be substituted in Kelvin. Okay, and this entropy generation is calculated in kilojoule per Kelvin. This is the mass, should be in kilogram, and this is the specific entropy in kilojoule per kilogram, kilojoule per kilogram Kelvin. And in this case, this heat transfer should be substituted in kilojoule. Okay, those are regarding the substitution. Type this term, how we can calculate S2 minus S1. I think we have learned this in the first revision class on chapter 7. We learned how to calculate delta S. So this is depending on the substance. So if the working fluid, if you do have, let's say, steam or refrigerant, 134A, so in this case I will be using tables. The condition at point 1 will be given, the initial state, and the final state should be given. Then we can calculate from the table S1 and S2. If it is actually when we do have incompressible substance, solid or liquid, so in this case we have developed an equation for calculation of delta S. Think delta S is equal to C average lim T2 over T1, and this is T average is T calculated from table A3 as average temperature. I think we have discussed this before. You can just look at the revision class. And in case when we do have the working fluid is gas, in this case you have to decide, you will be using actually the constant specific heat analysis, constant specific heat analysis. So we have developed actually two equations. You can just revise them, or we do have the variable specific heat analysis. So I will be telling you in any problem, either to follow the constant specific heat analysis, we have developed the relation. You can look at them, and also for variable specific heat analysis, we have developed the relation how to calculate delta S. Okay, if heat transfer, if the system is adiabatic, then this term actually will be 0. Type this in case when we do have a closed system. Okay, how to calculate the entropy generation within this system. Right, let's consider the case when we do have an open system, how we can calculate the entropy generation. So when we do have an open system, which is the second case, Usually it will be the same problem like on chapter 4 and chapter 5. That will be added actually in this chapter is to calculate the entropy generation. So for open system, when we do have an open system, let's consider the case when we do have a steady flow. So we do have a steady flow open system. In this case, actually, let's consider the rate form. So we can say rate of entropy S dot N minus S dot out plus the rate of entropy generation. This should equal to ds by dt for the system. The flow is steady, so this term is 0. Okay, so we can say the entropy generation will equal to rate of entropy out minus rate of entropy in from the system. Entropy out and entropy into the system, we do have two mechanisms, mechanism of heat transfer and mechanism of mass transfer. And based on that, for a steady flow open system, we can say the rate of entropy generation will equal to summation of M dot exit multiplied by S exit. This is the entropy transfer due to mass transfer, minus summation of M dot inlet multiplied by S inlet. And this is actually the entropy transfer due to mass transfer N, minus summation of Q dot, the rate of heat transfer Q dot K divided by Tk. And this is actually the equation that is applied to calculate the entropy generation for an open system. In this case, this is the rate of entropy generation calculated in kilowatt per Kelvin. This is M dot calculated in kilogram per second. This is the specific entropy, kilojoule per kilogram Kelvin. Okay, and this rate of heat transfer calculated in kilowatt. This temperature should be in Kelvin. Okay. Type this summation actually is the energy equation. This summation when we do have actually more than one inlet and more than one outlet. Like example for this one, also the same sign conversion rule applied. This is positive, negative, or in case of adiabatic system, this term will be 0, and this temperature is the surrounding temperature in most of the cases. And it should be given whatever the source or the sink of heat transfer. Type example when we do have actually like this, when we do have, let's say, mixing chamber. You can apply this equation exactly like the energy equation. Let's say we do have mixing chamber. We do have, let's say cold fluid and hot fluid are being mixed, 1 and 2, and then they are leaving actually at point 3. If I need actually usually for mixing the chamber, we do have internal heat transfer, but externally we don't have heat transfer, like what we have learned from chapter 5. Then we can actually calculate the entropy generation, rate of entropy generation will equal to, in this case, this term, Q is 0, so this term will be 0. So we do have summation of M exit, S exit, minus summation of M inlet, S inlet, which will equal to M dot, is in this case M dot. Okay, so it will be M dot exit, S exit, so M dot 3, S3, minus M dot inlet, S inlet, which is minus M dot 1, S1, minus M dot 2, S2. The main difference between the entropy balance and the energy equation, instead of S, it was enthalpy. And we have learned how to calculate this. At the given condition at point 1, we can calculate entropy S1. Given condition at point 2 and also at point 3, then we can calculate S2 and S3 multiplied by M dot, then we can calculate the rate of entropy generation. Okay? But this is regarding when we do have more than one inlet, more than one outlet. But when we do have single stream, like the flow actually through a compressor or turbine, single stream, so we'll just remove this summation sign. We do have mass in is the same as mass out, so we can take it as common. So in this case, the rate of entropy generation will equal to M dot multiplied by S exit minus S inlet, and we have to add here minus summation of Q dot K over Tk. The temperature, this term will be given for you, heat transfer. If it is adiabatic, the system is adiabatic compressor or adiabatic turbine, so this term will be 0. Otherwise, we can just add it, and here we can have M dot multiplied by S exit minus S inlet. S exit minus S inlet is the same, delta S. We need to calculate delta S. So also we look at the working fluid. If it is for the refrigerant, we have learned how to calculate S2 minus S1 at condition exit, can get S exit from the table. As the condition at the inlet, we can calculate S inlet. Then we can calculate delta S. If the working fluid is solid or liquid, we have learned how to calculate delta S from the equation. Delta S equal to C average ln T2 over T1. If it is gas, then we have to look if it is constant specific heat analysis or variable specific heat analysis. And in each case, we have learned how to calculate delta S. And then you can apply actually this delta S equation. Then we can calculate the entropy generation within the system. And this is actually the main use for how to calculate delta S that we have learned before. Type this in case when we do have a single stream. Type this is the case when we do have the whole case for actually when we do have a steady flow open system. Type when we do have unsteady flow. So in this case, for unsteady flow, we don't have the term of change of entropy of the system will not be neglected in this case, like the open system. So for unsteady flow, still we are working with open system, but the flow is unsteady in this case. So we'll just consider the whole equation. So in this case, we do have entropy in minus entropy out plus entropy generation. This should equal to the change of entropy of the system. A change of entropy of the system, which is equal to the final entropy, is final. We call it actually as S2, which is the final entropy minus S1. This is the total entropy, so which is equal to M2 multiplied by S2 minus M1 multiplied by S1. Then we can say the entropy generation will equal to just S in and S out. We can consider the summation sign, which is the general case when we do have more than one inlet or more than one outlet. So it should equal to summation of M exit, S exit minus summation of M inlet multiplied by S inlet minus, this is the mechanism of heat transfer due to mass transfer, minus summation of QK over TK, which is the mechanism of entropy transfer due to heat transfer, plus, please don't forget this term, M2 S2 minus M1 S1. And this is the equation used to calculate the entropy generation when we do have unsteady flow. Unsteady flow again, like when we do have a charging process or we do have discharging process. Let's say we do have a tank. This tank is to be filled, so this case is called the charging. Or when we do have a tank and we do have flow leaving this tank or leaking or something, so in this case is called discharging process. So this term actually makes it S exit. When we do have a charging, we do have mass in, but we don't have mass out. So in this case, this term will equal to 0 when we do have a charging, and this term will equal to 0 when we do have discharging process. Usually you will have only one inlet or one outlet, so usually the summation sign will be removed. The main difference here between the entropy balance and the energy balance or energy equation, you will look at the energy equation, you will find that instead of entropy here, it was enthalpy, and I think we have learned how to calculate enthalpy. It will be the same way how to calculate S exit and S inlet. So if it is a steam or something, you do have the condition at the exit, the leaving gas, or the condition at the inlet, then we can just calculate S exit or S inlet. Here is the final state of the system, S2, and the initial state of the system is S1. So the condition will be given. So at point 1, then we can calculate S1. At point 2, then we can calculate S2. And we do have M2 and M1, the relation between the mass is actually we do have mass in minus mass out is equal to the final mass M2 minus M1. This is the mass equation, if you remember it. So mass in, when we do have it charging, we do have mass in, but we don't have mass out. So mass out will equal to 0 in case of it charging. In case of discharging, we do have mass out, but we don't have mass in. So in this case, mass in will equal to 0. This should equal to M2 minus M1. If we do have a tank that is initially evacuated means M1 is equal to 0. So those are regarding M exit, M inlet, M2 and M1. We have to apply this equation to relate them. Then we can just take this equation and substitute here. Okay? So S2 is the final entropy, S1 is the initial entropy. If you remember, we said actually either we do have a charging or discharging, so S inlet or S exit can be calculated actually as the average temperature, which is T1, T inlet, which is T1, the initial temperature, plus the final temperature divided by 2. This is in case actually when we do have, usually when we do have a gas or something. But usually if you do have a steam or refrigerant, he will give you the condition directly. He will give you the condition either we do have a charging, he will give you the condition at the exit section, pressure and temperature. Then you can go to the table directly, calculate S exit or S inlet. But in case of gas, usually may not be giving actually the temperature at the exit, so you can consider the average temperature, which is T1, the initial temperature, plus T2 divided by 2, and then we can just take this temperature and go to a table from A17 up to table A25, so that we can calculate either S exit or S inlet. Okay, and that's all actually regarding how to calculate the entropy generation. So thank you.